In our daily life, we interact with audio devices almost without interruption. Whether we are talking on our mobile, watching a streaming series on a flat screen, conversing with our smart
Alexa,
speaker, driving in our car
play
with
the
music in the
news.
background, on a Zoom call, or listening to a podcast on our headphones while mowing the lawn, we are listening to or speaking to a device which has been evaluated and designed and tested in production to ensure that its electroacoustic performance will be acceptable to its end user. In this session, we will cover some of the basic measurements that are performed on these devices and discuss how they correlate with subjective opinions of the quality of the product. Before we get started, a brief biography is in order, so I'll provide it here. I'm Martin Alexander. I was born in and grew up in Brooklyn, New York, and I currently live in New Jersey with my wife, a slightly neurotic dog, Chance, and my Mazda MX-5. I have a bachelor's degree in mechanical engineering from Cooper Union, a small specialized school in New York City whose history is worthy of a lecture itself, and I have a master's degree from MIT. I worked as a sales and application engineer for Brulin Care for 35 years. Acoustics and audio was always in my blood from a very early age. In the 1960s, I played drums in a garage band and was also the AV nerd for the group. Here you can see me behind two of the other band members during a taping for RCA at the New York World's Fair in 1965. Here's a brief outline of what we plan to cover in the session, and thanks to John Barham, a former colleague, for the use of some material he developed for Brulin Care seminars. What is an electroacoustic system, and the consideration that this requires? What can we measure of the components or systems to characterize their performance? dB or not dB? Always a question. Electrical and acoustical parameters. Frequency response measurements, techniques and applications. Distortion measurements, what and how to make the measurements, and how it correlates with our perception of sound. Impedance, the electro in electroacoustics, and what does that tell us? And finally, we'll discuss basic directional characteristics of electroacoustic devices. First, let's define what we're talking about. An electroacoustic system contains one or multiple transducers, a medium for the transmission of acoustic signals, usually air, an enclosure for the transducers, which could be a speaker cabinet, a room, a performance hall, or a cell phone. We'll concentrate today on measuring the transducers. Then there is a signal, either the program material or some test signal, and finally the electronics which power or condition the electrical system and transmit it through the wires or the air or through RF transmission, either as analog or digital formats. How can we establish the performance of this system or any of its components? One way is a controlled jury test where a group of listeners rate the quality of the component. These listening tests are good in the sense that they provide a true measure of the quality of the device as would be perceived by people or the system and gives a subjective rating. But it can be difficult and time-consuming, especially during the development of a product. The alternative is a set of objective measurements where certain aspects of the device performance is measured. The hope is that the objective measurements reflect what listeners report subjectively. A listener might describe a speaker performance as overly bright, and perhaps the frequency response measurements of that speaker will show a relatively high level of response in the speaker's high frequency range. It is always the goal to make a measurement that reflects the subjective world. The search for a single number descriptor that correlates with subjective jury scores has always been a goal. POLCA, Perceptual Objective Listening Quality Analysis, is a widely used metric in the communication industry to evaluate overall speech quality of a device or network. In the audio industry, PEAK, or Perceptual Evaluation of Audio Quality, has its supporters. It is principally used to evaluate the effect of different audio coding schemes and sampling rates on perceived audio quality. In both cases, the reference signal and the graded signals are compared using perception models, and the resulting score is plotted on a 1 to 5 scale with 5 being excellent and 1 being bad. This scale is the same as the mean opinion score used in subjective jury testing and hopefully provides similar results. In one sense, they should correlate since the algorithms behind these rating schemes have been developed in part by training them using subjective ratings of a data set of samples which are mapped into the analysis of the same data set. These metrics are both useful but describe the effect of transmission and coding mainly and do not address the component performance. And that's what we want to look at today. The basic setup for an electroacoustic measurement is surprisingly simple. For a loudspeaker, a signal generator provides a calibrated test signal via an amplifier to the speaker under test. The signal is picked up by a measurement microphone, that is, a microphone whose sensitivity and frequency response is stable and well documented, with the signal then going to some type of an analysis system. Testing a microphone is the inverse. A calibrated sound source is fed a test signal via an amplifier, and the microphone under test picks up the signal, which is fed to the analysis system. The sound source is calibrated using the test setup shown in the previous slide so that its performance can be accounted for in the results of the microphone measurement. Of course, in today's world, the speaker or microphone may only be connected to the cloud, and driving it with a test signal becomes a bit more complicated. For now, we'll put that aside. Since we are measuring both acoustic and electrical signals, the first important issue to discuss is the decibel. The decibel. It's a great tool as it is a shorthand for describing signals relative to other signals. Basically, a level in decibel is 10 times the logarithm of a ratio of powers or parameters that are proportional to power. So, it could be a ratio of the square of 2 voltages or the square of the ratio of 2 sound pressures. While the decibel is a ratio of powers, most work in the field involves levels where the denominator of the log expression is some agreed upon reference quantity. So dBV refers to 20 times the log of a measured voltage relative to 1 volt, where the squaring of the voltage is moved out of the logarithm calculation and is a multiplier of the log ratio. Similarly, dBSPL is 20 times the ratio of the sound pressure relative to 20 micropascals, the approximate threshold of hearing. For sensitivities, their references, such as dB relative to a pascal per volt for speakers or relative to a volt per pascal for microphones, are used. For example, a microphone might be said to have a sensitivity of minus 25 dB relative to 1 volt per pascal. To understand how sound radiates, let's first look at a very simple case. A small source radiating into free space. The source is omnidirectional, that is, it radiates equally in all directions. The acoustic power of the source and the sound pressure at a point in space are related with the equations shown. Basically, it expresses the inverse square law. That is, the intensity, or the pressure squared, is inversely proportional to the square of the distance from the source. If we convert the equation using units of decibels, and to just make things complete, take the source inside an interior space where the sound is reflected from the surface to 1 degree or another, things get a bit more complicated. Here the sound pressure level, LP, at a point R away from the source is a function of the acoustic power of the source, the distance from the source, the directivity of the source, and the absorption of the surfaces in the room. In other words, how live or dead the room is. As the absorption goes up, the reverberant term becomes less and less important, and it is negligible eventually when we revert to what was the free field case. In a typical room, we can see that a speaker radiating sound can be measured with a microphone, but that the microphone will measure not only the direct sound from the speaker, but reflections from the walls, both early and late. The room becomes part of the electroacoustic system. If it is more reflective at certain frequencies than others, it will color the frequency response. To eliminate the effect of the room reflections, most electroacoustic measurements are made in an anechoic room where acoustically absorbing materials can be applied to the walls and ceilings, and in some case below an open grid floor to eliminate reflections and provide a free field, as you might have outdoors, but without the vagaries of the weather. Only the device under test, or the DUT, is measured in this case, not the enclosing room. Taking the simple case where we have a free field, say outdoors or in an anechoic chamber, we can relate the electrical power driving a speaker and the resulting sound pressure level we would read on a sound level meter. 1 watt of power into a 3% efficient loudspeaker, typical efficiency, would result in 30 milliwatt acoustic power, which, by using the equation from an earlier slide, would yield a sound pressure level of 94 dB at a distance of 1 meter from the loudspeaker. We can break up the types of products we might need to test into 1-port and 2-port systems. With a 1-port system, we cannot control the test signal. We can only measure the resulting signal, say with a sound level meter in the case of an acoustic source, or a voltmeter with an electrical source. With a 2-port system, we can introduce a signal of our selection and either know the content and level of the signal or be able to measure it, along with the resulting output of the device under test, so that we were able to characterize the system using the techniques and analysis systems in common use today, such as 2-channel spectrum analyzers or sine generators and voltmeters. Most of the measurements done in electroacoustics are measured using signals and analyses performed in logarithmic frequency steps or bands, such as octaves and third octaves. These correlate well with human hearing. The results of these tests are plotted on a log frequency axis and on a decibel or log level axis. The classic measurement setup is shown here. Although virtually all measurements today are performed using PC software, it is useful to understand the traditional components of a test system. In fact, many software-based systems today provide emulation of these components because of their usefulness and familiarity. The graphic level recorder in the diagram not only documented these measurements, but it also synchronized the other instruments. The signal generator provided a calibrated and known input to the test object, and the measuring amplifier, actually an acoustic calibrated voltmeter, provided the measurement output. The filter set could be used to improve the signal-to-noise ratio of the test, or to be used to measure distortion components of the device. We want our electroacoustic system to reproduce sounds accurately. In mathematical terms, we want it to be linear. Before we talk about frequency response measurements, we need to address some basics of linear systems and exactly what frequency response is. We can describe a linear system as one that follows several rules. If we introduce a signal, call it A, to a linear system, say an amplifier or speaker, and call it capital A out of the system, and similarly for a signal B introduced to the system, we say that a system is linear if when we introduce A plus B to the system, we get capital A plus capital B out. And similarly, if we introduce, say, 2 times A to the system, we get 2 times capital A out. We can therefore define the frequency response of a system as H, a function of frequency, which can be calculated as the ratio of the output of the system as a function of frequency to the input of the system as a function of frequency. The frequency response function is complex, meaning it has both magnitude and phase. If the system is linear, then the output for a given input will be simply the product of the input and the frequency response function. If the system is nonlinear, we will not only obtain the product of the input and the frequency response function, but also other, we can call them spurious frequencies. Basically, for a linear system, if we put a 1,000 hertz signal in, we get 1,000 hertz out. For a nonlinear system, we could get frequencies other than the 1,000 hertz input. An important aspect to keep in mind is that for a linear system, and measurements of the frequency response made with one type of signal, say stepped or swept sine, we will get the same results as for a different type of test signal, say broadband noise. When frequency response measurements are carried out, we have a measure of the fundamental or the linear portion of the response. While we don't usually associate the linear portion of response with distortion, if the response is not flat, there is distortion of the signal. The original spectral content of the signal will not be faithfully reproduced. An ideal frequency response is therefore typically thought of as a straight line. In other words, a response without any linear distortion. But keep in mind, the ideal response may be different from a straight line depending upon the eventual application of the device or exactly how it was measured. For example, a headphone measured with an ear simulator will not show a flat response since the simulator emulates the frequency response of the human ear, which is with its resonances and attenuations. If we provide a stepped or swept sine, each frequency at a known constant wattage or voltage to a loudspeaker, and measure the output in dB/SPL, we can plot the frequency response of the speaker in dB relative to an SPL per watt, or dB relative to a Pascal per volt. If we use broadband pink noise at a known given level and measure the result with a real-time analyzer, we should get the same response if the system being measured is basically linear. The signal used will not affect the measurement. If we have a dual-channel FFT device or software, we can use, say, a white noise signal and measure both the signal going into the device under test and out of the device, and thereby calculate the frequency response function directly along with other useful parameters simultaneously, say coherence and impulse response. Using this type of measurement effectively allows any test signal to be used, including program material such as speech or music. Now let's discuss nonlinear distortion, or what we typically think of as distortion. In this case, energy is transferred from one frequency in the input to the device to multiple frequencies in the output. The same classic setup can be used, but now the tracking filter is offset so that it measures the harmonic components and not the fundamental. The most commonly used measure of distortion is THD, or total harmonic distortion. It can be expressed in several ways, but is basically a ratio of the distortion component levels and the fundamental level, or to the total fundamental and distortion level. Legacy systems would often directly measure THD using a notch filter to remove, so to speak, the test frequency in the output and measure what was left, mainly THD. This technique would also include the system noise in the measurement since it was not measuring the discrete harmonics. While this was an appropriate measure of electronics performance, measurement of devices without any inherent electronic noise, such as raw loudspeakers, especially when measured in a production environment, could produce biased results, higher values for the total harmonic distortion than actually existed. Newer measurement systems, a more accurate measurement is typically made, where the individual distortion components are measured and later summed to provide the THD metric. Going beyond THD, understanding which components are dominating the distortion can provide insight into what the distortion process is and hopefully rectifying it in the final product. For example, these two data sets show in one case it is even harmonics that dominate the loudspeaker response, and in the other, odd harmonics. Each indicate a different potential fault. It is also important to note that because of psychoacoustics, all distortion is not equally audible. Because of the masking effect of the hearing process, the presence of a tone or signal at one frequency can mask other tones near it. This masking curve becomes broader as the masking tone increases in level. For high levels, the second harmonic can be inaudible at levels as high as 10%. Since the THD is typically dominated by the second and third harmonics, this may not affect the subjective assessment of the product. The higher harmonics, which although much lower in level, are above the masking curve and will be audible. Here's an example. The slide shows two loudspeakers. Subjective testing identified speaker 1, shown in the top graph, as good, and the other speaker as bad. Yet the top speaker has much higher THD dominated, as is typically the case, by the second and third harmonic. Speaker 2 has lower THD, but much more energy in the higher, more audible harmonics, 10th and above, the rub and buzz frequency range, so named since the sound of this distortion typically has a buzzing quality. For additional discussions of psychoacoustics and distortion measurements, be certain to join tomorrow's talk on rub and buzz and non-stationary loudness measurements. Some devices are band limited, such as mobile phones. This means that harmonics, especially those in the rub and buzz domain, will fall out of the device's passband. Other techniques are often necessary to characterize their distortion. Intermodulation distortion, where a fixed and moving frequency are used as test signals, or difference frequency distortion, where the test signal is comprised of two closely spaced sweeping tones. These signals reveal nonlinear distortion in the form of sidebands created by the distortion process. When using difference frequency distortion measurements, these components are closely spaced around the test tones and hence fall into the device's passband. In some cases, sine waves cannot be reliably used for testing at all. Devices with codecs, such as mobile phones, may not pass these signals reliably. They are optimized for coding speech, and the sinusoidal test signals may not be coded. In these cases, alternative test signals, such as modulated sine waves, narrowband noise, or multitones, may be used to estimate distortion. Another newer technique uses the power of multi-channel spectrum analysis. Coherence is a measure of the linear relationship between two signals. If the two signals, in this case a test signal and the measured signal, are identical, they have a coherence of 1 at all frequencies. Any nonlinear processes will show up as reduced coherence. We can then calculate a parameter, the continuous spectrum distortion, as a ratio of the non-coherent power and the coherent power. The calculations of this ratio are shown in the following slide. An example is a measurement of a hearing aid, shown here, where the calculated non-coherent power ratio can be expressed as minus 27 dB or 4.1%. Note that these percentages are not the same as THD percentages or related classic parameters, but do follow the general rule that the lower number is better. Just a note before moving on. Most of the examples we have provided here refer to speakers as the DUT or device under test. The same type of tests and measurements apply to microphones with certain complications. First, whereas there are many well-documented measurement microphones with practically immeasurable linear and nonlinear distortion that can be used to measure speakers, there are few calibrated, and I use the term here in a loose sense, there are few calibrated acoustic sources, and these sources require more extensive pre-calibrations to be used to test microphones. Typically, the technique involves a measurement microphone used near the microphone under test as a simultaneous or serial reference to establish the acoustic test signal levels. Further, distortion measurements of microphones are difficult as typical acoustic sources have higher distortion than most quality microphones, and to measure these characteristics of the microphone, several tricks, so to speak, are necessary. But that's the subject for a future talk. Continuing on, we can address impedance, in this case, the electrical impedance of a speaker. This is a frequently measured parameter in the laboratory during product development, and an even more common measurement on the production line. In the R&D lab, it is measured to determine the speaker's resonance frequency, a key parameter used in designing and evaluating the speaker enclosure performance, and to calculate the teal-small parameters. On the production line, impedance is a key measurement to ensure that the product is within spec. Impedance is defined as the resistance of an electrical circuit or component to alternating current arising from the combined effects of ohmic resistance and reactance. Although the impedance for a speaker is often quoted as a single number, say 4 ohms or 8 ohms, impedance is clearly a function of frequency. It is a maximum at resonance, since at that frequency the speaker has its maximum displacement and velocity and hence maximum back EMF, hence maximum impedance. So what do we mean when we say a speaker has an impedance of, say, 8 ohms? Typically, the rating is based upon the minimum impedance across the entire frequency range of the device, defined by the minus 10 dB points. The minimum impedance cannot be less than 80% of the stated impedance rating. For example, for an 8 ohm speakers, that would be 6.4 ohms. However, the use of this standard varies, and sometimes the speaker rating is just an average over the frequency range. The impedance curve provides insight into the performance of the device and the enclosure. Typically, the enclosure will have a lower resonance than the driver itself. There are 2 techniques to measure speaker impedance. Where a 2-channel measurement system is available, the voltage drop across the speaker and across a known reference resistor using a series circuit arrangement as shown can be measured. Knowing that the current through each component is equal, the unknown speaker impedance can be calculated using the voltage drop ratio and the known resistor value. Often on the production line, only a single channel measurement tool is available. In this case, a simpler measurement can be made. The voltage drop across the whole chain, both speaker and reference resistor, is measured. The voltage drop across the resistor has been measured as part of the calibration process, so it needn't be measured again during the actual DUT test. This provides for a simpler, less expensive, albeit potentially less accurate measurement. The test area I want to briefly touch on now is directivity measurements. Both microphones and speakers exhibit directivity, that is, different radiation is a function of direction. This is typically an effect that is more pronounced at high frequencies than low frequencies, as the wavelength of sound becomes comparable to the dimensions of the device under test. Depending upon the application, this may be a desirable aspect of the device or not. For example, while low directivity may be desirable in a speaker system of a home audio set or a smart device so that the performance of the device is less sensitive to the listener location, in concert systems, directivity can be desirable to make certain that the audience is sufficiently covered and there is minimum bleed outside the audience area. Microphone directivity is important in choosing the appropriate microphone for the application. For measurement microphones, we typically want an omnidirectional microphone, that is, one that responds equally to sounds from all directions through the entire frequency range, or at least the frequency range of interest. In pro audio applications, cardioid or supercardioid microphones may be desirable for the reduced sensitivity to sound from other than the main source, for example, a singer or a musical instrument. These microphones are often described as noise-canceling microphones because of their physics and performance. In modern devices such as cell phones and smart speakers, multiple omnidirectional microphones are used with software to provide a beam-forming effect and to yield dynamic directional characteristics and a high level of noise rejection. Directivity is typically expressed as the directivity factor, denoted as Q, that is, the ratio of sound pressure squared at a given angle, typically 0 degrees or on axis, versus the average sound pressure squared over 360 degrees. The alternative to Q is directivity index, simply 10 times the log of Q, providing the value in our old friend, the decibel. The directivity of a device is often displayed as a 2D plot cutting through the center of the device, showing the relative output as a function of angle, or a 3dB or balloon plot showing the data in a 3D display. Directivity measurements can be very time-consuming as they require measurements at multiple locations around the DUT. These measurements can be automated using a turntable, and in the case of balloon plots, a microphone array driven by appropriate software, allowing potential hundreds of measurements to be made with little operator intervention. Hopefully this short session, either as a first exposure to electroacoustic measurements or a review, has served to provide an understanding of some of the basic metrics used in the field. Electroacoustic measurements are not much different from electrical or acoustic measurements, just a bit more complicated. Understanding what they mean and how they correlate with perception is really the key. I hope you found this session useful as a jumping off point for working in this area. Thank you for attending and enjoy the rest of the program.